Welcome to the Deep Dive. Here, we cut through the noise and get right to what matters.
Absolutely.
We know you're busy, and you want to understand the essentials without getting bogged down in endless details.
We get it. That's why we're here. We are going to guide you to that aha moment, that feeling of really grasping the core concepts quickly and in a way that's actually, well, enjoyable.
Exactly. And today, we're taking you on a deep dive into the fundamentals of electric current, resistance, and circuits. Think of it as your express lane to understanding the chapter Current, Resistance, and Electromotive Force.
Yes. We're going to extract the key nuggets from this chapter so you can confidently understand how those electric charges behave when they're on the move.
And of course, we'll uncover the basic principles that govern those fascinating things called electric circuits.
All without overwhelming you.
Precisely. No need to drown in a sea of equations and technical terms.
So shall we jump right in?
Let's dive in.
All right, let's start with electric current. When we say electric current, what's the fundamental picture we should have in our minds? At its heart, electric current is simply the movement of electric charge.
Okay, movement of charge. Got it.
You can imagine it like a flow, much like water moving in a stream. And in most materials that conduct electricity well, especially metals, the things that are actually moving are those tiny, negatively charged particles we call electrons.
Right, those free electrons.
Exactly. They're like the little nomads within the material, free to drift around with relative ease.
So we've got this flow of electrons. But here's something that's always puzzled me a bit. I remember learning about the conventional direction of current. Why do we talk about current flowing in a certain way when, in reality, the electrons are actually moving in the opposite direction? It seems counterintuitive.
You've hit on a really interesting point, and it reveals a bit of the history of science. You see, before we even knew about electrons, scientists established a convention.
A convention?
Yeah, they agreed that current would be considered to flow in the direction a positive charge would move if it were under the influence of an electric field. And even though we now know that in most cases it's the negatively charged electrons that are doing the moving, especially in metals, this historical convention stuck around.
So it's like we're still using the old roadmap even though we've discovered a shortcut.
In a way, yes. So whenever you see a circuit diagram or you hear us talking about the direction of current, just remember we're typically referring to that flow of positive charge.
Even if it's the electrons going the other way.
Exactly. It's almost like speaking a language where some of the grammar rules are based on, well, historical quirks.
That's a helpful way to think about it. A historical quirk. Okay, so we have this flow of charge, but how do we actually measure it? How do we quantify it?
Good question.
I vaguely remember seeing a formula in the chapter, something about rates and time.
You're on the right track. Electric current, which we represent with the symbol I, is defined as the rate at which charge flows.
Rate of flow, okay.
Specifically, it's the amount of net electric charge, symbolized by dq, that passes through a given cross-sectional area over a tiny interval of time dt. And the formula that captures this is I equals dq divided by dt.
I equals dq over dt.
So in essence, it boils down to how much charge zips past a point in a certain time frame.
All right, that makes sense. Now, what about the unit? What's the standard unit we use to measure this electric current?
The SI unit for electric current is the ampere, often shortened to just amp or even simply the letter A. And it's named after a physicist, André-Marie Ampere.
Right, ampere.
1 ampere is defined as 1 coulomb of charge. That's a whole lot of electrons, by the way, flowing past a point every second.
So if we say a wire carries 1 amp of current, it means 1 coulomb of charge is passing through any point in that wire each second.
Precisely.
Okay, so that gives us a solid understanding of what electric current is. But the chapter also brought up this idea of drift velocity. And when I hear velocity, I picture something moving quite fast. Are those little electrons zipping through the wires at super speeds?
It's a natural assumption to make, but the truth might surprise you. While the electric field, which kind of nudges those electrons to move, travels through the wire incredibly fast, almost at the speed of light, the actual average speed of the individual electrons, what we call the drift velocity, is surprisingly slow.
Oh, really?
We're talking millimeters per second in a typical conductor.
Millimeters per second. That sounds more like a snail's pace than a lightning bolt.
It is quite slow. Imagine a crowded dance floor. People are bumping into each other, moving in seemingly random directions, but the overall flow of the crowd, say towards the stage, happens much more gradually.
That's a good analogy. So if these electrons are moving so slowly, how come when I flip a light switch, the light seems to turn on instantly, even if the bulb is a good distance away? It doesn't seem like those electrons would have time to travel that far.
That's a brilliant observation, and it highlights the difference between the movement of those individual charge carriers and the propagation of the electric field itself. Think of it like a wave in the ocean.
Okay, a wave.
Yeah, the water molecules themselves might only bob up and down a little bit, right?
Yeah.
But the wave, the energy of the wave, travels across the surface much faster.
Ah, I see.
Similarly, when you close that light switch, you're essentially establishing an electric field throughout the entire circuit almost instantaneously. And this field, this invisible force, is what acts on all the free electrons in the wire, prompting them to start drifting.
So it's the field that's fast, not the electrons themselves.
Exactly. It's this near simultaneous start of the electron drift throughout the whole circuit that leads to the light bulb lighting up immediately, not the speed of a single electron traveling from the switch all the way to the bulb.
That wave analogy is really helpful. It clears up that distinction.
Hmm.
So how does this slow drift velocity actually relate to the current we were discussing earlier? Is there a connection between those two?
Absolutely. There's a direct relationship between the microscopic world of those drifting electrons and the macroscopic current we measure, and it's given by a specific formula.
A formula, okay, lay it on me.
The formula is I equals N times the absolute value of Q times I times A. Now let's break that down so it's clear for you. N stands for the number of charge carriers per unit volume. So in our case, that would be a number of free electrons packed into the material.
Like how densely packed they are.
Exactly. Then we have Q, which is the magnitude of the charge of each individual carrier.
So for an electron, that would be the elementary charge, right?
You got it. Then we have Vd, which is that drift velocity we've been talking about, that average speed of the electron's drift. And finally, A represents the cross-sectional area of the conductor, essentially how thick the wire is.
So the formula ties together the number of charge carriers, how much charge each one has, how fast they're drifting on average, and the size of the pathway they're moving through.
Precisely. This equation beautifully shows how the microscopic behavior of those tiny electrons directly relates to the macroscopic current that we can actually measure.
It's amazing how these microscopic properties translate to what we observe at a larger scale. The chapter also mentioned current density. How is that different from just regular current?
Think of current density, denoted by the letter J, as a measure of how concentrated the current is within that conductor.
Concentrated, okay.
It's basically the current, I, divided by the cross-sectional area, A. So J equals I divided by A.
So it's like current per unit area.
Exactly. And what makes current density particularly useful is that it's a vector quantity.
Vector quantity meaning?
It has both magnitude and direction. For positive charge carriers, the direction of that current density vector is the same as the direction of both the drift velocity and the electric field that's driving the current.
Okay, so the current density tells us not only how much current is flowing, but also in which direction it's flowing.
Precisely. And for those positive charges, we can express this relationship mathematically as J equals N times IVD. Here, N represents the charge density, essentially how much charge is packed into a given volume.
So, to recap, current is the overall amount of charge flowing per unit of time, while current density tells us how that flow is spread out over the conductor's cross-sectional area and in which direction it's heading.
You nailed it.
Great. Now, let's shift gears to something that seems to be all about how much a material pushes back against this flow of current. Resistivity and conductivity.
You're right on track. Let's start with resistivity. Denoted by the Greek letter rho, pronounced rho, resistivity is essentially a material's inherent resistance to the flow of electric current.
Inherent resistance.
Imagine it as a measure of how much the material wants to fight the flow of charge.
Okay, so some materials are more stubborn than others when it comes to letting current pass through.
Exactly. Resistivity is defined as the ratio of the electric field, E, inside the material to the current density, J, that it produces. The formula is rho equals E divided by J.
A equals E over J.
So if a material has a high resistivity, you'll need a much stronger electric field to push the same amount of current through it.
Makes sense.
Think of it like water flowing through different types of pipes.
Okay, pipes.
Some pipes have rougher inner surfaces, creating more friction, making it harder for water to flow through. Similarly, materials with higher resistivity offer more resistance to the flow of charge.
So what units do we use to measure resistivity?
The SI unit for resistivity is the ohm-meter, written as ohm symbol dot meter, or eohm. And here's where it gets interesting. Different materials can have vastly different resistivities.
I can imagine.
For example, metals like copper and silver have extremely low resistivities, which is why they are fantastic conductors.
Right, that's why we use them for wiring.
Exactly. On the other hand, you have materials like glass or rubber, which have incredibly high resistivities, making them excellent insulators.
Yeah, they block the current from going where you don't want it.
Now, in theory, a perfect conductor, one with zero resistance, would have zero resistivity. Current would just flow through it effortlessly. And a perfect insulator would have infinite resistivity, completely stopping any current from flowing through it.
That's a great way to visualize the extremes. Now, what about conductivity? Is that just the opposite of resistivity?
You got it. Conductivity, denoted by the Greek letter sus, pronounced sigma, is simply the inverse of resistivity.
Inverse. So 1 divided by resistivity.
Precisely. It's a measure of how easily a material allows current to flow through it. The higher the conductivity, the better it conducts electricity.
Okay, so high conductivity means low resistance, just like with copper.
Exactly. And the units for conductivity are the inverse of ohm-meters, sometimes written as am to the power of -1 or Siemens per meter, sis. So good conductors, like those metals we talked about, have high conductivity, which corresponds to their low resistivity.
Makes perfect sense. Now, from our experience with electronics, we know that temperature can play a big role in how they function. Does temperature also affect the resistivity and conductivity of materials?
Absolutely. The resistivity of a material is generally sensitive to changes in temperature.
Sensitive how?
Well, for most metals, their resistivity goes up as the temperature increases. Think of it like this. At higher temperatures, the atoms in the metal are vibrating more vigorously, like they're at a wild party.
Okay, I can picture that.
And these vibrations act like tiny roadblocks, increasing the chances of collisions with those drifting electrons.
Ah, so more collisions, more resistance.
Exactly. This higher resistance translates to a higher resistivity. Now, for some other materials like semiconductors, things work a bit differently.
Differently.
Yeah, for them, the resistivity often decreases as the temperature rises.
So it gets easier for current to flow when it gets hotter.
Precisely. And that's because the extra thermal energy can actually free up more charge carriers, making the material more conductive.
Interesting. So that's why things like power lines might behave a bit differently on a scorching summer day compared to a freezing winter day. Their resistance changes with the temperature.
Precisely. And speaking of temperature and resistivity, the chapter even gave us a handy formula to approximate how the resistivity of metals changes with temperature. It's a linear relationship.
A formula, do tell.
It goes like this. T equals ×1 plus I times T minus T. Don't worry, it's not as intimidating as it sounds.
Let's break it down.
All right. Out T represents the resistivity at a specific temperature T as the resistivity at a reference temperature T. We usually take that reference temperature to be 20 degrees Celsius, which is around room temperature.
Okay.
And out, pronounced alpha, is what we call the temperature coefficient of resistivity.
Temperature coefficient of resistivity, all right.
This coefficient tells us how much the resistivity changes for every degree Celsius or Kelvin increase in temperature.
So it's specific to each metal, like a fingerprint.
Exactly. So this formula comes in handy when you're dealing with situations where temperature changes are significant.
That makes sense. And then the chapter touched upon a phenomenon that almost sounds like science fiction. Superconductivity.
Ugh, superconductivity. It's a truly remarkable phenomenon.
Can you tell us more about it?
It occurs in certain materials, but only when they are cooled below a specific temperature.
A specific temperature, like a threshold.
Yes, we call it the critical temperature, denoted by TCB. Below this critical temperature, something magical happens. The electrical resistivity of the material completely vanishes. It plummets to zero.
Zero resistance. That sounds incredible.
It is. Imagine current flowing without any loss of energy. It's a quantum mechanical effect, and it has the potential to revolutionize technology.
I can only imagine. More efficient power lines, super fast electronics, maybe even flying cars.
Well, maybe not flying cars just yet, but certainly more efficient power transmission, incredibly sensitive scientific instruments, and even levitating trains are within the realm of possibility.
Superconductivity sounds like a topic worthy of its own deep dive sometime. But for now, let's return to the more familiar concept of resistance. We've discussed resistivity, the inherent property of a material. But how does that relate to the actual resistance of a particular object, say a wire of a specific length and thickness?
Excellent question. The resistance of a particular conductor, let's say a wire, depends not only on the material's resistivity, but also on its physical dimensions, specifically its length and its cross-sectional area.
So a longer wire would have more resistance than a shorter one made of the same material.
Exactly. The formula for the resistance, R, of a uniform conductor is R equals R, the resistivity, times L, the length of the wire, divided by A, the cross-sectional area.
R equals L over A.
And this relationship makes intuitive sense. The longer the wire, the farther the electrons have to travel, and the more chances they have to collide with those atoms in the material, leading to greater resistance. On the other hand, a thicker wire, one with a larger cross-sectional area, provides more space for those electrons to move, like a wider road, allowing more cars to travel with less congestion.
So it's similar to how a narrow, long garden hose would offer more resistance to water flow than a wider, shorter one.
Precisely. And to measure resistance, we use a unit called the ohm.
Right, the ohm, symbolized by the Greek letter omega.
Exactly.
Yeah.
Named after Georg Simon Ohm, the ohm is defined as 1 volt per ampere. That's 1A equals 1 VA.
And this brings us to a very fundamental relationship in circuits, one that you've likely encountered before, Ohm's law.
Ah, yes. The famous V equals IR.
Voltage equals current times resistance. It's like the cornerstone of basic circuit analysis.
It's a fundamental relationship indeed. Ohm's law states that for many materials, the voltage across the material, V, is directly proportional to the current flowing through it, with the resistance, R, acting as the constant of proportionality.
So more current means more voltage if the resistance stays the same.
Precisely. But it's crucial to remember that Ohm's law doesn't apply to every material or every device.
So it's not a universal law like gravity.
Not quite. For some materials, the relationship between voltage and current is more complex, not a simple linear proportionality. We call those non-ohmic materials.
Okay, so it's more of an empirical observation that holds true for many common materials under certain conditions.
Exactly. It's a powerful tool, but it has its limitations.
And speaking of components designed to have specific resistance values, we have resistors. They're those little components we see in circuits, right?
Absolutely. Resistors are fundamental building blocks in circuits. They come in various shapes and sizes and are designed to have a specific resistance value.
And they're used to control the current in a circuit.
Exactly. By carefully selecting resistors with specific resistance values, we can control the flow of current in a circuit, divide voltage into smaller portions, and even generate heat.
Like in an electric heater.
Precisely. So resistors are essential for controlling and manipulating electrical energy in circuits.
All right, so we've discussed what makes charges move, that's our current, and what hinders their movement, which is resistance. But what actually sets those charges in motion in the first place, creating a continuous flow in a circuit?
That's where electromotive force comes into play. Often shortened to F and represented by the Greek letter epsilon, pronounced epsilon, electromotive force is what drives the current in a circuit.
So it's like the engine that keeps the current going.
In a way, yes. For a continuous electric current to flow, you need a source of energy that can keep pushing those charges along. And that's precisely what EMF does. It provides the electrical pressure, so to speak, that keeps the current flowing.
But even though it's called electromotive force, it's not really a force in the same way we think of a physical force pushing an object, right?
That's an important distinction. You're right.
It's more like creating a difference in electrical potential, like a hill that the charges roll down.
You've got it. EMF is really a measure of the energy per unit charge that the source can provide.
Okay, so it's more about energy than force. And what's the unit we use to measure EMF?
The SI unit for EMF is the volt, V, just like electric potential difference.
So we can say a battery with a higher EMF can deliver more energy to the circuit.
Exactly. Now, an ideal source of EMF in a perfect world would maintain a constant potential difference across its terminals regardless of how much current is flowing through it.
But in the real world, batteries and other power sources aren't ideal, are they?
You're right, they're not. In reality, all sources of EMF have some internal resistance, denoted by the lowercase r.
Internal resistance.
This resistance is inherent to the device itself. It's like a bit of friction within the source, arising from the materials and the processes happening inside it.
So even the source itself resists the current to some extent.
Precisely. When current flows through a real source, there's a voltage drop across this internal resistance. It's like a small toll that the current has to pay. This means the actual voltage you can measure across the terminals of the source, the terminal voltage, is a bit lower than the ideal EMF when current is flowing out.
Ah, So the internal resistance steals a bit of the voltage.
Exactly. We can express this relationship mathematically with the equation VAB, which is the terminal voltage, equals A, the amp minus I times R, the current times the internal resistance.
VAB equals A minus R. Got it.
So you can see that this internal resistance acts like a small bottleneck, reducing the ideal voltage that's available to the external circuit.
It's like a leaky faucet, reducing the water pressure.
A good analogy. And this internal resistance also affects the total current that flows in the entire circuit.
It does. How so?
Let's imagine you connect an external resistance R to a source that has an EMF and an internal resistance R. The total resistance in the entire circuit is the sum of those two resistances.
R plus...
Now, according to Ohm's law, the current, I, that flows through the whole circuit is I equals A divided by R plus R.
I equals A over R plus R.
You can see from this equation that the internal resistance in the denominator reduces the overall current compared to what it would be if the source had no internal resistance at all.
So the internal resistance acts like a bit of a drag on the current, limiting how much can flow.
Exactly. Now let's talk about energy and power. Once we have current flowing through a circuit and voltage differences across different components, we inevitably start dealing with energy and power. How do we quantify the energy being used or delivered in these circuits?
Great question. I know power is a key concept when we talk about electrical devices.
You're absolutely right. Power, in the context of circuits, essentially tells us the rate at which energy is being transferred, used, or generated.
Okay, rate of energy transfer.
When an electric current, I, flows through a circuit element that has a voltage difference across it, VAB, the power P, associated with that element is given by P equals VAB times I.
Power equals voltage times current.
Exactly. The SI unit of power is the watt, W up, defined as 1 joule of energy transferred per second. So a watt tells us how many joules of energy are being moved around every second.
So a 60-watt light bulb uses 60 joules of energy every second.
Precisely. Now let's consider a simple resistor where Ohm's law applies. How do we typically think about power dissipation in that case? You might have noticed that resistors often get warm or even hot when current flows through them.
Right, so where does that energy go?
Well, in a purely resistive element, the electrical energy is converted into thermal energy. That's why those resistors heat up. We can express the power dissipated as heat in a resistor using Ohm's law, substituting VAB with I times R.
So we get P equals I squared times R, or we can also write it as P equals VAB squared divided by R.
Exactly. These formulas are essential for understanding how much energy is lost as heat in a circuit, and also for designing components that can handle that heat without failing.
It's important to make sure things don't overheat and melt. Now, what about the power associated with the amp source itself? How does that factor into the overall energy balance of the circuit?
Excellent question. Let's consider an EMF source, like a battery, that's supplying current to a circuit. The rate at which this source converts non-electrical energy, like chemical energy in the case of a battery, into electrical energy is given by amp times I, the amp times the current.
So that's the total power the source can potentially deliver.
Right. But remember, the source has that internal resistance, so some of that energy gets dissipated as heat within the source itself.
Lost internally.
The rate of this internal power dissipation is am squared times R.
So not all the energy from the source makes it to the external circuit.
Exactly. The net power output of the source, the power delivered to the external circuit, is the difference between the total generated power and the power lost internally.
So it's am minus I.
Precisely. And interestingly, this net power output also equals the terminal voltage, VAB, which we defined earlier as I minus R times the current I.
So it's VAB times I, which matches our general power equation.
Exactly. It all ties together beautifully. Now, what happens when we flip the script and actually put energy into the EMP source, like when we charge a battery?
Recharging. How does that affect the power dynamics?
In this case, the current flows in the opposite direction through the source.
Opposite direction, you mean it enters the positive terminal and exits the negative terminal.
Precisely. And when this happens, the terminal voltage, VAB, across the source becomes greater than the EMF.
Greater than the F.
Yeah. The relationship becomes VAB equals I plus R.
VAB equals I plus I. Interesting.
And the power that's being supplied to the source for charging is VAB times I, which expands to I plus IR.
So we have two terms here.
Right. The A term represents the rate at which energy is being stored in the source, like chemical energy being replenished in a battery. And the IA term, well, That still represents the rate of energy dissipation as heat due to the internal resistance.
Ah, so even during charging, some energy is still lost as heat.
Unfortunately, yes. Now let's discuss a situation that can be quite dangerous, a short circuit.
Oh yes, short circuits, I've heard those can be bad news.
They can be. A short circuit occurs when a low resistance path is accidentally created across the terminals of a voltage source. It's like creating a shortcut in the circuit, bypassing the intended load.
So the current takes the easy route.
Exactly. In this situation, the external resistance in our circuit, R, becomes very small, almost zero.
And what happens then?
Well, if we look at Ohm's law, I equals I divided by R plus R, when R becomes extremely small, the current I in the circuit can become very large. It's essentially limited only by the internal resistance of the source, so I becomes approximately equal to I divided by R.
So a tiny resistance leads to a huge current.
Precisely. And this huge current can cause a lot of trouble.
Trouble how?
This huge current can lead to very high power dissipation within the source itself, as well as in the short circuit path. Remember our power equation, P equals I squared times R.
Right.
Well, with a huge I, the power dissipation becomes enormous. This can generate excessive heat, causing components to overheat, potentially leading to damage, fire, or even explosions.
That sounds scary.
It is a serious concern. That's why we have safety devices like fuses and circuit breakers in our electrical systems.
They're designed to interrupt those dangerously high currents, right?
Exactly. They act like safety valves, preventing catastrophic damage.
Good to know. So far, we've been talking about current, resistance, and F from a macroscopic perspective, looking at the overall behavior of circuits. But the chapter also delved into a microscopic model, trying to explain what's happening at the level of those tiny electrons within materials.
Ah, yes. The classical model of metallic conduction. It's a simplified model, but it provides a good starting point for understanding how those free electrons in a metal give rise to electrical current and resistance.
So what's the basic idea behind this model?
Well, in this model, we picture the free electrons within a metal as moving randomly, much like gas molecules zipping around in a container.
So they're bouncing around chaotically.
Exactly. They constantly collide with the positive ions that make up the metal's lattice structure. However, when we apply an electric field across the metal, it introduces a bit of order into this chaos.
How so?
The electric field exerts a force on the negatively charged electrons, causing them to experience a small net drift velocity in a specific direction.
Opposite to the direction of the electric field.
Precisely. And even though this drift velocity is incredibly slow, as we discussed earlier, it's this collective drift of all those electrons that constitutes the electric current we observe.
So the electric field gives those randomly moving electrons a slight nudge in a particular direction.
Exactly. And now let's see how this model helps us understand resistivity. What causes the resistance in this microscopic view?
That's a great question. If those electrons are essentially free to move, why do they encounter any resistance at all?
Well, according to this model, the resistance arises from those constant collisions between the drifting electrons and the positive ions in the metal's lattice structure.
Ah, so those collisions act like tiny roadblocks, slowing the electrons down.
Precisely. Every time an electron collides with an ion, it loses some of the energy it gained from the electric field. It's like constantly bumping into obstacles while trying to run a race.
Makes sense. So the more frequently these collisions occur, the higher the resistance, and therefore the higher the resistivity of the material.
You got it. And this model even gives us a theoretical formula to calculate resistivity based on these microscopic properties.
Oh, what's the formula?
The formula is Rus equals divided by nut. Don't let those symbols scare you. Let's break it down.
Okay, I'm ready.
Earth is, of course, the resistivity. Represents the mass of a single electron. N is the number of free electrons per unit volume, so it's essentially how many free electrons are packed into the material. A is the magnitude of the electron charge. And finally, R, pronounced tau, is the mean free time, which represents the average time an electron travels between collisions with those ions.
So a longer mean free time means fewer collisions, right?
Exactly. And according to this formula, a longer mean free time would lead to a lower resistivity, making the material a better conductor.
It's amazing how this model connects the microscopic world of electrons to the macroscopic property of electrical resistance. It's like zooming in to see the tiny interactions that give rise to the big picture.
It is quite remarkable. Now, it's important to remember that this classical model, while insightful, has its limitations. It doesn't fully explain all electrical phenomena in materials, especially those that require quantum mechanics to understand, like superconductivity.
Right, sometimes we need more advanced tools to explain the truly bizarre world of quantum physics.
But despite its limitations, this model provides a valuable framework for grasping the basic mechanisms behind electrical resistance. It helps us bridge the gap between the world of tiny particles and the everyday electrical properties we experience.
Well, I think we've truly taken a comprehensive deep dive into this chapter on current, resistance, and electromotive force. We've covered a lot of ground, from the definition of electric current and drift velocity to the intricate relationship between resistance, resistivity, and temperature. We've explored Ohm's law and how it applies to simple circuits, delved into the concept of EMF and the role of internal resistance, and analyzed the power dynamics in circuits. We even ventured into the microscopic world to understand the origins of resistance in metals.
We've systematically addressed all the major points, theories, findings, and examples presented in the chapter. And now, armed with this foundational understanding,